One other type of reaction we're going to talk about here in Chapter 4 that occurs in aqueous solution is what's known as a precipitation reaction. The name for this comes from this term of a precipitate, which is a solid that forms in a chemical reaction. And one way you can remember this name is it's like precipitation that falls from the sky. A solid that forms in an aqueous reaction will fall out of the solution onto the bottom of the beaker or test tube or whatever you're doing the reaction in. So if you have, say, a mixture here and you pour in another chemical, if a precipitate forms, you'll get a bunch of particles and they'll all drift to the bottom, kind of like rain falling from the sky, except for it's a bunch of solid. And so precipitation reactions are a really important part of chemistry and another important thing that we can look at with aqueous reactions. Now, to understand precipitation reactions, we have to first talk about the idea of soluble versus insoluble ionic compounds. And I use the word insoluble here, but even insoluble compounds dissolve a little bit in water, but just not enough to an appreciable amount. So your book uses the term, I believe, sparingly soluble or slightly soluble. We're just going to call it insoluble to make it clear, to make this distinction. And I will also just mention up front that this is a relative scale. So there's a whole spectrum. There are things that are kind of in between soluble and insoluble. But for our purposes, for right now, we're just going to classify things as either soluble or insoluble and call it good. And so a soluble compound is one that separates into ions in solution. So an example of sodium chloride, if you put it in water, it will separate completely into sodium ions and chloride ions. And none of the solid remains behind, so when it dissolves. So let me be clear, and here we're talking about, not ionic equations, but ionic compounds. So sodium chloride being an example of a soluble ionic compound, when you put salt into water, it completely separates into the sodium and chloride ions, and they get surrounded by the water molecules. An example of an insoluble compound is something like silver chloride. This will not dissolve in water. So if you weighed out silver chloride, put it into water, it would just stay as a solid. Or if you make silver chloride in a reaction, it will turn into a solid if those silver and chlorine find each other. So does not dissolve in water, stays as a solid. So this difference between soluble and insoluble compounds is what drives precipitation reactions. So in precipitation reactions, or in these aqueous reactions, we're often starting with two soluble compounds, we mix them together, and an insoluble compound forms, and a precipitate falls out of the solution. So how do we know what's soluble versus insoluble? I picked a couple of examples that I know off the top of my head are soluble and insoluble, but how can you know that in advance? Well, there are rules that we can follow that have been observed over many years of chemists working with ionic compounds that tell us whether something will be soluble versus insoluble. So I'm going to go ahead and put those up. This is a slightly different list than what you have in your textbook. It's the same basic outlines. There's a few extra ones here that are not in your textbook. There's a few extra ones in your textbook that are not here. We're mostly going to stick to the ones on this slide here, to be consistent with all the sections of general chemistry, to make sure we're all using the same sort of set of solubility rules. And this is not all of the possible solubility rules that we have, but this is a good starting point. And these I will provide to you on an exam. You don't need to worry about memorizing these, but you should be familiar with them so that you have an idea of whether something is soluble or insoluble. And you can double check by looking at the rules, but you should be familiar enough with them that you can get most of the way there. So soluble compounds, we can group them by cations and anions. All cations of alkali metals and ammonium ions are soluble, with no exceptions. So anything with sodium, lithium, potassium, anything in that first column of the periodic table, all compounds involving those cations are soluble. On the anion side, our always soluble anions are nitrate, acetate, and perchlorate. And there are no exceptions to those. All of those dissolve. We have some other anions where most of the compounds that form from them are soluble. These are chloride, bromide, and iodide. Those are generally soluble, with a few exceptions being silver, lead, mercury 1, and mercury 2. And then sulfate, generally sulfates are soluble with the exception of, again, silver, lead, mercury 1, mercury 2, and then now we also add calcium, strontium, and barium to this list. So those are the things that are usually soluble with some exceptions. On the other hand, we have some anions, I should say, where most of them are insoluble, and there are exceptions that are soluble. So that's down on the bottom half of our chart here. So we have the oxide anion. There are no exceptions. Oxides that form from NH4 plus and alkali metals react with water. So they don't really dissolve in water, they react with water. So there are no exceptions. Anything that forms an oxide will be insoluble. Sulfides are insoluble with the exception of compounds of ammonia and alkali metals, right? So all the ones listed on the top half under soluble compounds, and then the same thing goes for carbonates, oxalates, phosphates, and hydroxide, with the exception of for calcium, barium, and strontium hydroxide. Those are soluble, and those will all form strong bases as well. So this is our general solubility rules. In the next video, we're going to look at how we can use these to make predictions and look at how precipitation reactions can happen.